Hey there and welcome to my channel. My name is Rayan Al-Yusuf and today I'm going to explain to you how to capture energy in a fusion reactor. I'm going to begin from elementary heat and energy transfer all the way up to electromagnetic wave propagation. I'm going to explain it as clear and simply as possible with some fancy visuals I created myself as well. So if you're a physics fanatic like myself, I think you'll thoroughly enjoy this video. Let's do this. Alright, let's begin with the basics and work our way up. I have put timestamps in this video, so if you're like, I already know this stuff, skip ahead. You probably already do if you went to grade 5 and 6. We're talking about conduction and convection. Take two cars, for example. Say you have one car parked in a parking spot, he's still. And another car comes down, looking at his phone, not paying attention, and crashes into that car. That car is going to transfer all of its kinetic energy, a lot of it at least, into that still car, and it's going to push it some distance. Those are like particles. Particles have kinetic energy, and when they collide, they transfer it. But in reality, no particle is stood still in a parking spot. Every particle is constantly vibrating and moving at least a little bit, unless you're in absolute zero temperature, like space. So in that case, when these two cars are moving toward each other, the one with greater kinetic energy is going to end up moving the other instead of the slower one moving it. Alright, so that was a bit of a refresher on grade 5 and 6 basic heat transfer. And one thing you'll realize they had in common is conduction and convection rely on a medium to transfer their energy. They both rely on the collision of particles and some kind of medium there to transfer their energy through, their kinetic energy. But what if there's no medium? What if we're talking about the sun transferring its heat to us, or a fusion reactor, where this plasma is confined and the closest components on the front wall are on the other side of a deep vacuum? Well, this topic I hinted at the beginning of the video, electromagnetic wave propagation. Stay with me here because it isn't the complex topic that it sounds like. Electromagnetic wave propagation begins with charged particles. When you have a charged particle like a proton or an electron, these are going to have electric field. The electric fields are radiating out of that particle. But what if you move that particle? Say you have a proton with an electric field radiating out of it. If you move the particle, the electric field is going to lag behind it slightly. That's because the electric field is only radiating out at the speed of light. The information of the change in position lags behind. So what happens is you create a wave in that electric field. And a phenomenon we discovered back in the early 1900s is when you create waves in an electric field, you create a magnetic field. And the same happens with magnetic fields. If you have an object creating a magnetic field and you create a wave in its magnetic field, it's going to create an electric field. So this very interesting phenomena where electric fields changing and magnetic fields changing both create each other is what allows energy to propagate back and forth in what we call electromagnetic wave propagation. And inside a fusion reactor where we are confining plasma, the plasma itself is filled with these charged particles. That's what a plasma is. If you don't know, a quick rundown, a plasma is what you get when you heat up a gas so much, you give it enough energy that the atoms separate into their neutrons and protons, the nuclei, and the electrons. So now you have positively charged nuclei with the negatively charged electrons. We do this so that we can manipulate the plasma with electromagnets and confine it. But moreover, you now have plasma filled with charged particles that is radiating electromagnetic waves constantly as these charged particles accelerate and decelerate around the orbit of that tokamak. Alright, now that we understand how energy can be produced and can traverse a vacuum like from our sun to ourselves or through the vacuum of a fusion reactor, let's go into some nuances because this is far from the only heat source you are dealing with. In fact, there's another major heat source that I hinted to earlier that is produced in these fusion reactors. We call that neutron radiation. You see, when we ionize a gas and make it a plasma, We break it up into the nuclei, which is protons and neutrons, and the electrons. Both of these have some kind of charge, and they both are going to be manipulated by the electromagnets and get confined into the plasma. But what about the neutron that is produced in the fusion reaction, that byproduct neutron? Well, it has no charge, so it cannot be manipulated, and it will easily fly out of that plasma with its great amount of kinetic energy, in fact about 14.1 mega electron volts. That's most of the energy produced in a fusion reaction between deuterium and tritium. And it's going to fly with its kinetic energy until it hits the front wall of the reactor or ceiling or floor somewhere. And it's going to put all of that kinetic energy into the wall in the form of heat. This is very troublesome because the neutrons can have different reactions with the materials, and most of the time you don't want that to happen. It tends to degrade the material. So you have to deal with that. But on top of that, you have to capture this heat of the neutron so that we can have successful fusion energy. On top of that, there's another form of conduction that takes place in the fusion reactor in a very unique scenario. In this fusion reaction of a deuterium and tritium atom, we don't just produce a high energy neutron, we also produce what we call an alpha particle. That's a helium-4 nuclei. And helium-4 is a larger nuclei than the hydrogen isotopes we fuse in a reactor, and because of their greater mass, they are going to orbit the center of the tokamak with a greater radius. That greater radius will make the plasma less dense, and because helium-4 isn't contributing to the reaction, it's not producing any more energy, we don't want that. We want to get rid of it. That's why we call alpha particles in fusion reactors nuclear ash. We want to get rid of it. How do we do that? Well, we can take advantage of that relatively larger orbit by sucking it up right from the bottom of the reactor. That's what we call the divertor. By manipulating the electromagnets, we can bring the plasma lower toward the divertor, where the helium-4 can be selectively removed momentarily without disturbing the plasma too much. But during the execution of removing this nuclear ash, the plasma can contact a lot of the components, and conductive heating can occur quite rapidly and intensely. A lot of that heat can go into the components, and we need to remove that. That is an intense surge of heat right there. All right. Thank you guys so much for watching. I hope you went away with some fascinating knowledge to share, and I hope your brains are a little bit bigger after that lesson. This has been energy production and transfer in a fusion reactor, and I have more fusion energy related videos to come. But until next time, I've been Rayyan Al-Yusuf. Thank you.